You can start when you're ready, okay?
Okay. Okay. Hello everyone. Today I'll present a paper called FairBatch Batch Selection for Model Fairness, and the paper is published in ICLR this year. I want to say like in this talk I will introduce some background of fairness and also introduce this paper, and based on the slides are based on the tutorial of this tutorial in KDD. The deep learning is widely used to glean knowledge from maximum amount data. So there are lots of applications. For example, in NLP, social NLP, Google Translate here, and also healthcare to detect some disease, and also the self-driving car, and also game. For this big success of deep learning, we can consider two game changers. The first one is big data. You can see this chart, and the amount of data in this world is expected to grow to 175 data bytes in 2025. And to explain this set, if we can give an example, like if you assume a cup of coffee, there is a cup of coffee as 1 gigabyte of data, and the 1 gigabyte of data is approximately the 1 Great Wall of China. The second game changer is faster computation, and application processors in smartphones are faster enough to run various deep learning applications, such as this speech recognition for virtual assistants. And also Google announced the TPU for the first version this year. It performed more than 100 petaflops. And also deep learning can be accelerated using TPU. And AlphaGo is also equipped with TPU also. Along with the proliferation of the AI applications, there has been a growing concern on gender, race, and other types of bias in this system. For example, severe bias against African American encompass to score the criminal defendants for race-based risk. This compass is a tool, is a system, is a case management system, and used by the U.S. court to assess the likelihood of a defendant becoming a recidivist. And many Black defendants are predicted to be at a higher risk of recidivism, but fewer white defendants are predicted to be at a lower risk of recidivism. The bias can exist in many shapes and forms, and can be introduced at any stage in the model developer pipeline. And the bias can show up in several forms, for example, word data here. For example, in data, it includes some like data have some heuristical bias, representation bias, something. Even if we have perfect data, our modeling method can introduce bias. For example, the evaluation bias occurs during the model iteration and evaluation. And a model is optimized using the training data, but its quality often measured against certain benchmarks. The bias can arise when these benchmarks do not represent the general population, or the benchmarks are not appropriately for the way the model will be used. So even if your model is making correct predictions, a human reviewer can also introduce their own biases when they decide whether to use some or to accept or disregard the model's prediction. So what is a fairness? In many ways, the fairness in AI are two sides of the same coin. There is no universal agreed upon definition for fairness. We can broadly defined definition as the absence of preference for individual or group based on their characteristics. There are most of the global fairness fall into 3 fairness criteria: independence, separation, sufficiency. These criteria are defined in the Fair Machinery book, and the independence defined like this one. The y hat is independent to z. And what is y hat? Y hat is a model prediction, and y is a true label, and z is a sensitive attribute. For example, the gender, race, something. So for the independence says that like the y hat, the model prediction is independent to the sensitive attribute, which we can call like is called demographic parity, and also the separation says that like a y hat is independent of z given y, which is exactly can be called like equal as the oath. And also sufficiency is saying that the y independent of z given y hat, which is called the predictive parity in the previous literatures. I will introduce this definitions one by one, and given some research works on using these definitions. And also the first I will introduce is the demographic parity. So the objective here is to obtain that the sensitive groups have the same positive prediction rates, just like this equation here. Y hat is a model prediction. For example, model predict recidivism, and Z here is the sensitive attribute, bad person or black person. And one equals to D equal to 1 or 0, and Y hat equals to 1 or 0 is a prediction. And like this one, if we want if we want to compare the probability of y hat being 1 and the positive rate, and we want to make sure these two values are the same for different groups, the white groups and the black groups. And so the fairness is so to achieve this is the demographic parity is simple, but it's used in several applications, including predicting crime and hiring, and also giving loans. The second fairness measures I'd like to introduce is called equal as the oath. This measure extends demographic parity as this one as following. It can still want to ensure the sensitive group. The sensitive groups have the same positive prediction rate, but for 2 cases, the label equals to 1 or 0. The formulation is similar to the demographic parity, but the difference is they have a new condition here. Y equals to A belongs to 0 and 1. The rest of formulation is the same. And the intuitively the equal as the oath is to try to distinguish the qualified from the unqualified people. The third measure is fairness measure is called predictive parity. Compared to the equal as oath, the role of y and y hat are swapped here, and we want the sensitive group to have the same positive label rates when the prediction is 0 or 1. So in the formulation, we can see y and y hat are exchanged compared to the equal as the oath. So why do we want to use this measure? Is because when we want to ensure the model's precision rate to be the similar for sensitive groups. These are all 3 common used fairness measurements. So I will first then introduce some common unfairness mitigation techniques. To addressing the data bias in the literature, the literature can be introduced, can be classified into 3 classes. The first is kind of a pre-processing, in-processing, and post-processing. Depends on whether the bias is mitigated before, during, and after the model training. So the first we introduced the pre-processing approach. I just try to fix unfairness before the model training. There are pros and cons. The pros are that you can solve the root causes of unfairness and assume that unfairness comes from the training, from the bias data. On the other hand, it might be tricky to ensure the model unfairness, model fairness actually improves because like we don't have access to model training itself. Even you do some fix on the data, it's not clear if the model is going to benefit. But there is still a lot of workers on these pre-processing approaches. They can be classified into 3 approaches. One is the first one is like a repair whatever data you have. The other approach is to generate a fair data from the data you have. And the third one is to acquire new data from outside to make your training data fair. So I'd like to introduce to explain what doesn't work and what does work. There is a naive approach is to mitigate the unfairness is to remove the sensitive attributes. For example, there is attributes in the adult data set, name, zip code, age, race, gender, and income, something. Just to do the pre-processing approach, maybe we can just reduce or get rid of these attributes. Not use these attributes to do the model training. So the problem is even if we remove these attributes, sensitive attributes, and we can still using some other attributes to infer these values. For example, the zip code is known to be correlated with race because the people with similar race tends to live in the similar zip code. So if you have if you have hair credit score, it is an indicator that you might have more income. So this removing the sensitive attributes directly is not work. The next approach I will introduce is in-processing. This approach is try to fix the model for fairness during the training process. And the pros are that you can directly optimize accuracy and fairness. And the cons that you may have to make a significant change and in the model training, which may be not feasible in many real applications. So there are large 3 in processing approaches. There are 3 main classes. The first one is add a fairness constraint. So we can optimize the both accuracy and fairness in the training for the training process. The other approach is adversarial training, and that's we can leave the model as itself, but we compare it with another model that tries to figure out the sensitive value in an adversary fashion. So this way, it will force the model become more fair. And the other one is adaptive rewenting. And the idea is to give different ways to the input sample examples so that the model training efficiently has just they have unbiased input data. I will introduce here. I will introduce an example to works on at fairness constraint and adversary training. For the fairness constraint, this work is a well-settled work proposed by Zafar. And the goal here is to try to maximize the accuracy with the fairness constraint for convex margin classifier. And a margin classifier is the margin classifier is one that like using the decision boundary and the distance from decision boundary to data points, and which is called them to maximize the margin for the training. That means maximize the distance between any the distance between the decision boundary with the data samples. And here we want to satisfy the demographic parity as much as possible. However, the question is the demographic parity itself cannot be expressed as a convex constraint. So this paper, they use proxy instead. The proxy is the covariance between the sensitive attribute and the assigned distance to the decision boundary. And more institution, why this works. For example, like here we have two cases for the model classification here. And we are trying to classify the circles versus the squares. And let's say that the colors, the orange color and the blue are the sensitive, orange color and the blue one are the sensitive attributes. In the good case, the covariance is 0. Since you can see that the colors have really nothing to do with which side, and you can which means which side like maybe you are on the decision boundary, and on the right side you see a bad sense, like a bad case, right? And most of the blue points are on the side on one side of the decision boundary, which means the covariance either positive or negative. So making the covariance equal to 0 or close to 0, we can ensure that the sensitive attribute is more independent of the prediction, which exactly the demographic parity. The second approach is called inter-adversary or debarrassing. And the idea is to compute the two models here. And here is a model, like is the human model here, and try to predict the recidivism or not. And it's all output yes or no. And there is a discriminator, the adversary. The adversary discriminator tries to glean the sensitive attribute information from this yeses or no's. And here they're trying to see if this person is black or white. And if the model is wildly training, then like you will end up with a predictor that again really good at that is really good at having a sense of information, and the adversary that's really good at discrete the races, and that's exactly satisfy the demographic parity. The final approach is for unfairness and mitigation. And the mitigation is post-processing. And we want to fix the model predictions for fairness. The pros are it may be the only option if the data and the model cannot be modified, because that maybe you don't own the applications, or you cannot access or modify anything due to the legal reason. On the other hand, the model, the post-processing usually results in a worse accuracy because you're adjusting the final model. So I will introduce this paper. They propose a FairBatch, a batch selection for model fairness. The idea is to try to perform fair sampling during the batch selection. And this approach can be classified into in-processing approaches, but it actually does not modify the training algorithms. So it's actually much easier to deploy. here is some like the motivation I'm going to go through in this class. Things like more and more model training commonly employs some batch selection to get mini batches from the training data, and the random sampling is often used to select the mini batches. Like we have training data, and we have many mini batches here. We run our model and during each batches at each epoch to accelerate the training process. In this setting, like it's not a good idea to just taking the random. Maybe the random sampling for mini batches, especially like if the training data is sparse. You can see training data like most of data belong to a sensitive group 1, and only several data samples belong to the sensitive group 2. So if we consider random sampling, the mini batches are going to stay sparse. So this lead to unfair model predictions, right? This maybe lead to unfair model predictions. So the solution in this paper is to adaptively select the mini batch size for the purpose of improving the fairness, and it's done by adjusting the batch sizes with respect to sensitive groups based on the fairness and intermediate models. So what this means? That means that after we have after iteration 1, we have intermediate model, right? And if the group 2 is discriminated, and the fair batch will increase the portion in the next mini batch. And this is the main idea here. So look like the idea you can see is very straightforward, but the challenge is how to find the optimal ratio, and that leads to best fairness. So the key feature of the fair batches are twofold. The one is to adaptively select the mini batch size to improve the fairness internally, and also it solves a bi-level optimization for fairness and accuracy. It can be employed with a single line change of PyTorch code, and the performance result is pretty good. It can obtain the higher accuracy and fairness within one training, and also it's run much faster than the fair training based science. And finally, it can gracefully merge with existing batch selection techniques used for faster training, like importance sampling. So I will introduce more detail. This slide I will introduce some background or like in the parameter notions used in this paper. The W here is a model parameter, X is the input feature, Y hat is a predict class, and Y and no hat is the ground truth class. Z here is a sensitive attribute like gender or something. They consider a 0-1 loss. That means defined as this equation. If the prediction is wrong, the loss equals to 1, and M is the total number of training sample. And using this notion, so we can get the overall impair risk of the deep learning model defined like this one. M like average of all the losses of the training data. And they also, things like they introduce sensitive attributes, right? They define a new type of a new variable to L1ZW is called the empirical risks, again aggregated over the sample subjected to Y equal to Y and Z equal to Z. What does mean? This means like Y, for example, if Z, for example, Z equals to for example, it's a binary sensitive attribute, male or woman, and 0 and 1, we can get the overall risk for the men part and the woman part, and overall we plus these two risks together is the overall historical risk. And they also here we introduce like how they translate the mini batch SGD and the batch selection into a bad level optimization solver. And so consider a scenario that like which one is to minimize the overall empirical risk LW through the mini batch SGD. The mini batch SGD algorithm try to pick a B of M in data sample uniformly at random, and update this iterate with batch gradient. And this batch gradient is unbiased estimate of the true gradient of this empirical risk. In like because they consider uniformly sampling around. Once the mini batch distribution is not from the uniform distribution, the batch gradient estimate is not anymore an unbiased gradient of the true of the overall empirical risk, right? So instead is unbiased estimate of related empirical risk. So like for example, if we draw a training example I with probability pi for all I, we define the summation of pi equal to 1. The batch gradient is an unbiased estimate of the weighted risk, and pi is a weighted risk here. And more like in this way, we actually we have like a bad level optimization with mini batch SGD. In a uniform sampling way, like we first define the mini batch sampling distribution like this one here, uniform sampling. And for each epoch, we draw the mini batches according to the mini batch sampling distribution. And for each mini batch, we do the gradient descent and update the mini batch sampling distribution, this bad level optimization. And so this is algorithm of that the previous slides. And in order to integrate the fairness criteria during this process, they consider to define the bad level optimization like this way. The P here is the distributions of the probability of the sampling probability of each data sample P1 to PM, and the cost here is to find the best sampling distribution to minimize the cost. Like here, they consider the fairness cost, and the WP here is the empirical risk minimization with width, which is try to increase the accuracy. So you can see this is a bad level optimization solver. So like at the initialization, the mini batch SGD will optimize an unweighted empirical risks based on the outcome of inner optimization, and will define the WP, right? And then they will draw the mini batches like this one to continue training, and finally training this whole process until convergence. The problem is how to design a cost function to capture the fairness criteria, and how to design the update role for the outer optimization. I mean, we know how to update this inner objective using mini batch SGD, right? And how do we design the outer objective for outer optimizer? So okay,
what is the W below the argument? I understand WP's definition.
Okay.
But I'm curious, what is W below the argument? Yeah, it's that.
The y hat here, y hat is a prediction, right? The y hat is a prediction. The model prediction is a function of model parameter with the input feature. It's inside of the model prediction.
Okay, so WP is also like kind of weights.
It's model parameter. It's
Model parameter from the SAT, model parameter SAT, right? Okay, from the
yeah,
batch.
yeah,
Okay.
that's fair.
So the model parameter, this W here, it's a SAT or something? According to algorithm 1, the W.
You mean it's a set?
Because you need to choose you make a WP, you choose something from the W, right? You get a WP through
No, Dr. Actually, it's just that
it's like
actually they define. You
Uh.
see, in this iteration, they get a model parameter. They train this model. When you one iteration, they get a new model W, right? They
Yeah.
define this WP as this W as a WP because the data distribution is changed. Something. It's right.
Oh, okay. The change
don't
is
know.
not from it's not from W, it's from the P, right? Okay,
Yes.
it's
How
from
do
the
they sample
probability.
in the batch?
How do you sample the
change?
batch?
Yeah.
Okay. Oh, it's weird. In that case, should we put the P below that? Okay, yeah, I got what you mean. Okay. All right, yes, please continue.
Next I'll introduce like how do we define the cost and the the outer objective and the inner objective based on two different fairness criteria. For example, the equalized oath. The equalized oath trying to enforce the prediction to be independent from the sensitive attribute conditional on the row and the true label. And here the true label, right? And in the so like we have these relationships when we're using the empirical risks. Again, introduce the LYZW is empirical risks aggregated over the samples subjected to y equals to y and z equals z. And here this one is y equals to 0, z equals 0, and y equals to 0 and z equals to 1. Thus they try to, this means the empirical risk is the same when the prediction, when the class, when y equals to 1 is but the different, but I mean two sensitive groups is the same, and also for this one. They using this information, they try to propose strategy to adjust the sampling probability between L00W, L01W, and the sampling probability between L10 and L11. So to achieve this one, they build a new build a bad level optimization like this, like here, and they try to draw a sample in this way. They pick the set y equals 0, z equals 0 with probability lambda 1, and the set y equals to 0, z equals to 1 with probability this one. And also the set w, the set y equals to 1, 0, z equals 0 with w2, and on the rest the rest of them. They build 3 sets, and they pick one data at random from the chosen set, and to define the weighted and probable risk. And then they put this equalize the odds as an objective function here to reduce the equalize the odds here. And yeah, this is how they show how they use equalize the odds to build the bad level optimization problem. And when they
sorry, I also got confused by this equation. So It use the mean, then the max within the big prime bracket.
Yeah,
This
actually,
definition somehow I can understand, but they use W lambda, and lambda is defined as argmin. If you
no,
put it, yeah, also all these solve the W lambda equals to argmin to this equation. I really, so the W lambda here equals to argmin something is a definition or is
it's the same in this way. They just want to put this together. That's like they first gave a model at the beginning, W lambda, right? And because they don't know at the beginning, they don't know how the sampling probability will choose in the beginning, right? So they just made random initialize to W1 and W2 and generate and solve the model, get a W lambda, and then use this model, try to minimize this loss and get a new lambda, and put this new lambda, new sampling probability in this loss function, and get a new model, and the new model put here, and get a new sampling probability, and continue to random model. Not some point. Maybe this is not the correct or the formal math definition for the problem, but they try to define this in this way.
Yeah, from your explanation, I can understand the procedure, but I just if mathematically, if you put those things together, I don't know how to solve this.
Good question. I will show. I will like introduce how they solve this one.
So what is the M0 star, M1 star? What's those?
Yeah.
What do you mean?
Yeah, I will introduce that. M here is a total number of data samples, right? Total number of the data samples, and here like M0, because like this is the binary classification. We only have the ground truth label classes only have two cases. Y equals 0 and Y is equal to 1. So they count the number of the samples with the 0 label and at the M0 star. They don't care about the sensitive attribute. And here M1 means they count the samples with labeled as 1.
The total.
Yeah, total. This is total. This is total. Total number of data. The overall trained data set, the total is a total number of data set is M. And some, because it's binary, right? Some of the data is have the label equals 0. Some of them equals to the label equals to 1. So they try to count how many data equals to 1, how many data equals to 0. The label
0 and 1 here. Oh, okay. Okay. Yeah. Continue, please. I just feel very confused if you put everything together. Yeah.
This is they put this paper. They put the things like this one. They show is a paper. And then I will introduce they consider the demographic parity, which is satisfy the if two sensitive groups have the equal positive rate, and they show that in this case the empirical risk should in this have this relation. The L00 equals L01, and it's somehow it's different in the equalize odd. Equalize is odd is 0 equals to 0, 1, and this equals to is the same. Or maybe I make a mistake here. Or let me see. Here I'm sorry, I make a mistake here. This is I forgot to change this one. It's changed at 1, 0, 1, 1. There is a mistake. Sorry. And to satisfy this condition, they try to adjust the sampling probability between L00, L10, and also the sampling probability between L01 and L11, and get this bad level optimization problem. So somehow the same, similar things with equalized O's but the difference is the here and here. And in general, for FairBatch, the general form is like this one. And they have optimization. The outer objective is to achieve fairness. F and G, you can treat like two groups, and they try to measure the impact risks over two groups. And the constraint here is they try to get the impact risk, the weighted impact risks over this two sensitive group. And they solve this optimization problem by designing a signed gradient-based optimization. So because they show that under some conditions, the FW function is quasi-convex, and there is a global optimal solution. So they design this sun gradient-based optimization to approximately finding the optimal point, the optimal sampling probability. And so the algorithm itself is simple. They just need to adjust the lambda values depend on here, and which sensitive group is being discriminated. Therefore, this is how they solve this problem.
Well, yeah, then we have to trust the mathematical magic they have there.
Yeah, we have to trust. They prove that, and they prove the FW in some case is convexity, and they choose that. Next, I've introduced how they integrate their method in the code library. And this is a typical sample code for model training. It includes the data loader and epoch define and input data optimization, output and loss define, loss backward and other optimization steps. And if we take pre-processing or input processing approaches, we have a lot of work to do. It requires the non-trivial changes either in the data generation or the algorithm design this part, and both of which may be infeasible in practice. So this paper, they only need to replace the sampler with the one-line code FairBatch. There is a function, and so their algorithm can be easily deployed in existing machine learning pipeline. I will introduce the experiment setting.
No. I want to know. I know you introduced the theoretical part, right? So I still want to know if you want to really execute it, right? So what's the sampling procedure? What's the steps you need to follow, right? So okay. It's not like, when you do the coding, it's not like you do an optimization, right? You want to make it simple, and there are a few steps and procedures you can follow. Right?
Yeah, I know. They have. I forget to. Let me show. I forgot to put it here. They have actually. So it's quite simple and intuitive. For example, like for here, you can see the screen, right? They try to adjust the sampling, the lambda with respect to equalized odds. And the input is the intermediate model and the criteria and the training data. That's train, Z train, Y train, and also the previous lambda and the FairBatch learning rate alpha. And they first get the output of the model training, and then they define the loss, and they define the distance, the group, the difference in the group, the loss here, the mean of equal to this one, and also define the loss left here. And then if because if D1 is 0 more than D in this constraint, they update in this row, and else they define in this row. And the only changes in the paper is how is only change I think, for example, in this way is how they define, how they get this value here, this area.
So the lambda is not solved by optimization, right? It's only do some simple comparison.
It's iterative for them.
Oh,
It's
see,
iterative.
no. What I'm saying, trying to say, I mean, from a previous mathematical deduction, my image is, you need to solve the optimization to get the lambda, right? But here you just use a very simple steps to iteratively get the lambda. Okay, here is
yeah, they have, because they define the sum here. This is a loss, the difference, right? And G double lambda and F double. This is the D they show, and they solve this.
Okay, that one is consistent with their optimization solution.
Yeah, here, for example, in F1 double lambda here, G1 double, it's the same.
Okay. I think probably the biggest magic is how can you build up this kind of relationship, right? So makes this overall complex thing to be looks like a simple iterative steps updates of lambda. Yeah. Okay. Yeah. I know the equation you show me. Yeah, this one is consistent with that one. But I think the biggest thing is I want to build up bridge between, the lambda J, F J, George J equation with previous optimization. Yeah, that's the thing. Okay. Anyway, yeah. Okay.
So in the experiment settings, they consider two data sets. The first one is compass, the second one is adult sensors. And they consider the gender as sensitive attribute. They consider the model logistic regression. And also they consider two fairness measures equal as the odds and the demographic parity defined like this one. And this is an equation for that. And so there is a result. This table compares the FairBatch against another baselines on the comparison and adult census with respect to the accuracy and fairness and complexity, or in number of epochs. And they consider three tables baseline when non-fair training with logistic regression, fair training with the pre-processing, fair training with in-processing, and although their approach FairBatch. And for pre-processing approach methods, they consider rewinning and label bias correction. Rewinning is a method to try to balance the importance level across sensitive attributes, sensitive groups through the example weighting. And but they keep this weights through the intermodal training, unlike the FairBatch here. And the label bias correction iteratively training trains an entire model with example weighting towards an unbiased data distribution. And the input processing method, they compare with adversarial disbiasing, as I mentioned before, is an adversary learning approach that intends to maximize the independence between the predicted label and the sensitive attributes. And they also consider ADA boost-based fair training, which is an ensemble technique. We can see the result here. The pre-processing technique here, they reduce the ED, the equalized order disparity, but sacrificing the accuracy performance and also require a lot of epochs. And also the pro-processing further reduce the unfairness, but still satisfy the accuracy, and it requires a lot of training epochs here. And but the proposed FairBatch can achieve a comparable or even greater fairness performance while sacrificing less accuracy, and also very efficient. The similar comparison over the demographic parity and fairness here, and we can see the fairness batch achieves fair, accurate, and fair and accurate result efficiently because with the smaller epochs. They also show the FairBatch can be merged with the existing batch selection approaches. The existing batch selection approaches using some like importance sampling for faster convergence training. The key functionality of the importance sampling is that the examples considered to be more important are given care weight. So the important weight, the important sample will be sampled more frequently. So FairBatch can be easily merged with these approaches. Here is the result when integrated with the important sampling. We can see that the FairBatch using using much like a 50 favor epochs to converge to the low disparities compared to not using the weight. So the conclusion is that this paper improves the model propose a FairBatch method. The FairBatch improves the model fairness and accuracy efficiently with one line change of code. And the idea is trying to adaptively select the batch sets to improve the fairness using by-level optimization. And the FairBatch can be easily merged with the existing batch selection technique used for faster convergence. Thank you. That is this paper. Any questions?
Any questions?
Thanks, Jiahao. I have one question.
Sure.
Yeah. So for the EPRM results and for the algorithm, it's only for one sensitivity attribute, right?
Yeah.
So if the sensitivity attribute is 2 or multiples, the proposed algorithm cannot work. Or
no. Yeah. Good question. I know. I know. Maybe you will. I mean, some guys will ask this question. I show their paper. They show that
okay.
like if beyond the labels, not binary, or the beyond the sensitive attribute, not binary attributes, they can still do the optimization method. This is the by-level optimization. They extend, for example, the minimize the sampling rate lambda, and the maximize is I equals 1 to D. That means they try to maximize the here the I is each dimension, and they extend the binary to the multi-dimensional. They introduce like a lot of laws in each dimension. So this is their method to handle the beyond the binary labels and the binary sensitive attributes. They do
But-
not do the experiment to. I don't think they do experiment beyond the sensitive attributes more than one. They don't do experiment.
But in this way, it maybe cannot work, because you mean that one code have multiple attributes, so the sampling rate for one code for different attributes may be not same according to the equation, right? So lambda I is for multiple attribute, right? The sampling rate.
Yeah, you are
Yeah,
right.
yeah.
Alright.
But when you do the experiment results, the sampling for each result record, it should be same. Yes.
Yeah, you are right.
Yeah, yeah, yeah.
Maybe it will affect some. Yeah, I mean, based on like I understand point, but I think like because their algorithm is iterative based around is but based on design. Maybe I think maybe enough long time it may be achieve a better trade-off for fairness and accuracy longer than something, because it's not a very accurate sampling since we introduce more dimension, right?
Yes. So another question is about the fairness rules. So the fairness rule that you mentioned in the field page, the former page. Yeah, there are 3 rules. So the 3 rules, I think they are also for one attribute. So
yes, you are right.
So when they want to use these rules to design to extend the algorithm, so it should be for one attribute. Yeah, because
but actually it's the same. Because like this demographic parity can be easily integrated into multi like dimensional, right? If it's for example, if z equal to race, different race, we can still do that. Like we just need to consider like a y equals 0, but z0, z1, z2, z3, z3, all the probability equal together, right?
Yes, or maybe another attribute except z.
Yeah.
Okay.